warahmatullahi wabarakatuh and salam sejahtera. In my previous lecture, I already discussed with all of you about improving performance of Rankine cycle. The motivation is even small increase in thermal efficiency can mean large saving from the fuel requirement. And the idea of this motivation is the average fluid temperature should be as high as possible during heat addition in a boiler, and average fluid temperature should be as low as possible during heat rejection in a condenser. So, the idea is to increase the temperature. First thing first, we have to superheat the steam to higher temperature. And secondly, to increase the boiler temperature. Next, the idea of to lowering the temperature is by lowering the condenser pressure. Okay, next we go on how we can take advantage of the increased efficiency at higher boiler pressure without facing the problem of excessive moisture at the final stage of the turbine. So, if we can see here, if we increase the boiler pressure from state 3 to state 3 prime, we can see that the moisture will increase from state 4 to 4 prime. And how to overcome this? First thing first, we have to superheat the steam to very high temperature before entering the turbine. And secondly, expand the steam in the turbine in 2 stages, which means we use 2 turbines, and reheat in between, and this process is called reheat process. This is the schematic diagram of the ideal reheat Rankine. Pump, boiler, high pressure turbine HPT, and low pressure turbine LPT. So we use 2 turbines and condenser. The liquid or steam will enter the pump and it will compress and it increase the temperature as well as pressure. So if you see at the TS diagram at state 1 to 2, this is isentropic compression and it will cause the temperature getting higher. So in a boiler, what happens is there will be heat addition. So in state 2 to 3, this is constant pressure heat addition. So this is highest temperature, T3. T3 is the highest temperature and this is at the inlet of HPT turbine. So at the HPT turbine, there will be isentropic expansion where we can say that S3 is equal to S4. Okay, so if we can see at T4, the temperature is still higher compared to T2. So it is a waste if we release this temperature to the atmosphere. So what happens is we reheat this temperature in a boiler, or we send back this steam to the boiler. So in a boiler, it will reheat the steam and the temperature of a steam will increase to T5 here. And we can see here that the temperature is increased from T4 to T5, and usually T5 is equal to T3. Okay, so T4, this is state 4 and this is state 5. 4 and 5 is occurs at constant pressure, and this process is reheat. Okay, so the pressure, the liquid will enter at the state 5 at an entrance of LPT here. Okay, so again in this LPT there will be isentropic expansion as 5 is equal to S6. And what happened is the pressure will reduce to state 6, okay, as well as temperature. Okay, so now we concentrate on state 2, state 3, state 4, state 5, and state 6. So in state 2 to 3, this is constant pressure heat addition. Okay, since this is reheat Rankine cycle, so we call this process heat addition process as a Q primary. Okay, so this is Q primary, H3 minus H2. And there will be one more heat addition, okay, at state 4 to state 5. Here, 4 to 5, where the liquid is reheat in a boiler. So here 4 to 5, and we call it as a Q reheat. So Q reheat is H5 minus H4. So this is the total heat input. Okay, next, since we have two turbines, HPT and we have LPT, it means we have two work output, one from high pressure turbine and one from low pressure turbine. So work output for high pressure turbine represent with H3 minus H4 plus work of LPT H5 minus H6. So for thermal efficiency for reheat, we have WHPT plus WLPT, low pressure turbine, minus with work of compressor and dividing with Q in, Q primary and Q reheat. That's all for reheat Rankine cycle. Thank you.